Uh-oh.
Yeah, so just be careful not to distress the camera.
So these are 1 billion year old granites.
I want to show you, you've got the three types here. Cut by the dark black dikes here, which are from when, and you see bigger ones behind us, when things are rifting apart. But additionally, here you've got a pegmatite, and this is the third kind of dike. This got in place last, and pegmatites, they're the very, very last things to form when a melt is solidified, and you get these very, very large crystals forming in them, here we have a pegmatite. So yeah, they often have volatile rich residues and can concentrate rare elements, and these are the last bit, and these pegmatites are often forming in magma chambers that are beneath continental rocks, which this is. This is the continental margin of Arabia. But of course, Arabia at that time was part of Africa, which at that time was part of Rodinia, or part of Gondwana, which is part of Rodinia. So what we are now thinking of Arabia didn't exist. This is too far behind. But you've got three very different types. You've got a pegmatite dike there, you've got the sort of basaltic extension dikes here, and you've got the original granite that got made, the continents coming together, the continents drifting apart, and when this is sometime after all of that, you've had pegmatite in place. All of it somewhere between 1 billion and 800 million years. And obviously this is oldest, that's the middle, and that's the youngest. So these time range that they were in place.
Yes. Just from the field station. I'm not very
magma to form big crystals. It's basically when you get pegmatite.
It must have been at a time when
This is the first stop on day 7. We're really excited because this is Precambrian. It's granite with pegmatite dikes and basaltic dikes. This is part of the ancient continent of Rodinia, and what makes this really a great spot, and you can see in the distance, is the intrusions, all of the various layers of intrusions. So these are about billion-year-old rocks, but they're a little different. We're now in eastern Oman, and in reading the Gustav Hoffmann field trip guidebook, these outcrops, even though they're Precambrian, have arrived at the surface very late. They're Eocene uplifted. So these are not involved in the Somal or the Haracene naps. These, now that we're on the east side of Oman, these are more influenced by the later abduction that we're going to see in the what is called the mother of all outcrops. There's going to be a different compression and different structural uplift. And in the distance, James has pointed out, there's Miocene. As we come up and around towards Sur and all along the northeastern coast of Oman, we're going to see tertiary sedimentary rocks, and because of the rebound and uplift, we're going to see deep incisements. So we're working our way up to the coast, but we're starting here in the basement.
Well, it's interesting to be here in Oman and see some of the oldest rocks in Oman, which are about 1 billion years old. And of course, as James pointed out, there are other places with much older rocks like Scotland at 3.5 billion, and we were in Minnesota, which was 3.8 billion. But 3 billion year old or 1 billion year old rocks are very important. We have some around the New York State area. This isn't a granite, but in Enchanted Rock, for example, as I picked up a pegmatite off the ground here, it does look a little bit like Enchanted Rock. And Enchanted Rock is a granite that's about 1 billion years old. It's in central Texas, not Oman. But we all think about things when we look at rocks, what we've seen in the past, and how we're going to put it together in a bigger story. This is Kimberley.
I'm just saying it built up a CO2. The longest story.
It's a red shirt and a black kimberlite that
Well, that's what a kimberlite is. It's different. As the pipe has been bursting up through everything, it's been entraining material into it, and this is all the material that it entrains. Ripped out of the walls as the explosion is ascending up. So I think that's what's characteristic.
Those carboniferous black.
Well, it's not that it's carboniferous. It's oh, you mean it's carbon containing?
Yes.
Because it,
This is a carbonatite. Or no, it's a kimberlite. It's a kimberlite, but it does not have any diamonds in it.
Rushing up. Yeah, but this piece on the ground is very nice. Rushing up, explosion. All the sides of the wall, the sides of the tube. Yeah, it's all full of. I don't know if I should rush back to the car and get my.
So this is the Radiolarian Church. And the kimberlites are boulders that have rolled down from the hill.
So here at the northeast coastline of Oman, we are standing on the beach, and we are looking here at a carbonatite. It's either kimberlite or carbonatite. It's been called both. But the important thing is that this is a diatreme from the lower mantle, and it's full of all kinds of ultramafic rocks that are in conical form, and it's got inclusions of lots of different rock types, perhaps also including the lower crust. And this happened at the, as many of the kimberlite dikes do, at a continental breakup, and this one was in when Gondwana broke up. And roughly there's two different age dating techniques. It ranges, the age of this was incredibly rapid. In a matter of days, which is a geologic instant, it traveled from 100 kilometers deep, and it came up in a matter of days, and this forcefully injected itself. And this is an incredible, it's about 200 meters around, and this is the kind of thing where diamonds are found elsewhere. No diamonds here, but there do appear to be carbonate rocks included in here from the deep mantle, which is kind of something to think about. So, very special place.
On a beach in Oman, looking at a fabulously interesting rock. This rock here is known as a kimberlite. Kimberlite is named after Kimberley in South Africa. These are the famous diamond forming pipes where carbon dioxide had built up at depth, maybe 200 kilometers deep, caused an expansion and caused a volcanic eruption to explode up to the surface. But this pipe here in Oman is slightly different to the ones in South Africa. One of the differences in South Africa, the erosional level is quite low, so the rock is all compacted, whereas this one, rock has actually come out and erupted at the surface and fallen down. And we're going to see some of these accretionary lapilli on the summit there where they've been falling down. And another key difference is it actually doesn't contain diamonds. But one more difference as well, this has actually a lot more carbon in it, so it's actually a sort of carbonatite rich kimberlite. But follow me, let's walk up this kimberlite. And I'm going to come right up onto the top here. Right up onto the top here, keep coming. And looking down here, can you see these round circles? These round circles are the accretionary lapilli. So as this was rushing up, the explosion actually came out into the air, and this material was falling back down to the ground, and it's made this deposit. So a kimberlite that is actually quite an unusual kimberlite, but a very important rock. Tell you about it, and then we can stand back and take the pictures, and then of course people can invade the scene and you can start getting pictures of yourself there, and it is possible when we go and take pictures to stand in front of it. You can also come around and stand on the top of it as well, but just for now I'm just going to tell you about it, and then we can take some pictures. So I'm gonna read what I've written as a starter. So this spectacular fault is this spectacular and highly photogenic fault is informally known as the mother of all outcrops, and that's because that guidebook we showed you, the author of the guidebook, he got his students to kind of vote on a name, and that's what they came up with, and the name is stuck. It's even on Google Maps. We've even got this geoheritage sign now. It's one of Oman's most famous geological exposures. It forms part of the Batane Nap, which was abducted together with the Masra ophiolite some 15 to 20 million years after the emplacement of the Somal ophiolite. And that's why you've got this intense fold, because rather like the Holocene sediments that were intensely folded. Anyway, the rocks belong to the Wahara Formation and are late Jurassic to early Cretaceous in age. They consist of strikingly alternating red radiolarian chert, you see the red colour, and white porcelainite. And these were deposited in a deep ocean setting at water depths of approximately 4,000 to 5,000 meters. And at these depths, carbonate sediments cannot accumulate, so you don't get corals and limestones, things like that. But radiolarians, which are planktonic protozoa with silica brackets opal skeletons, they can continue to thrive, and when they settle down they can be preserved in water of this depth. Now porcelainite, which is the white, is an impure, less fully silicified form of chert containing clay and carbonate, and represents an intermediate stage between siliceous ooze and a fully recrystalline chert. Now, the distinctive red and white banding is one of the most eye-catching features of the outcrop. These layers, though, are thought not to be annual varves. They're not annual layers because the accumulation of radiolaria is far too slow for it to be annual. So it's thought that instead they reflect longer-term changes in ocean conditions, such as variations in silica productivity, clay or carbonate input, and bottom water oxidation. That's the word I'm looking for. Now, so basically, these could be Milankovitch cycles. Do you know what Milankovitch cycles are? Some people didn't. The Earth, its tilt changes, its wobble changes, its ellipticalness changes. You plot all these together, you've got the ice ages and interglacials. And these are Milankovitch cycles, and they can cause, you know, changes in the ocean, changes in. So basically, in certain conditions, there might be more radiolaria than others, and this is reflected in the patterns. So the red colour is linked to iron oxides formed under more oxidizing conditions, while the white porcellanites reflect. Oh yeah, so basically once this is started, then there's the process of diagenesis, and that kind of, when it turns into rock, it exaggerates it, and kind of all the red kind of concentrates together. So the red colour is linked to iron oxides formed under more oxidizing conditions, while the white porcellanites reflect differences in sediment mixture and degrees of silicification. Now, going on and on, the absence of turbidites, together with a relatively high clay content, indicate that deposition occurred in a distal ocean basin. What that means, it's in an ocean basin kind of like behind the spreading ridge, or behind. It's not kind of, you don't get to it just by turbiditing off the shelf. And far from continental slopes and major sediment input, these original flat-lying pelagic sediments were later caught up in the plate convergent and the Napa placement. That's why they're folded. So structurally, the outcrop displays intense folding and faulting. So you can see the clear fold here, but look, if you look just to the sort of right of it, there's fault there, and then there's a vertical, there's another fault, and the more you look at it, you see more and more faults there, as well as the fault. It's a structurally the outcrop displays intense folding and faulting, with beds folded into tight, almost reclined chevron folds requiring hinge collapse visible in the fault cores. Folds are cut by minor thrust faults formed during the compression, as well as later normal faults. Right, that is all from me. Yeah, that's a fold.
Linda's our talking.
This is the cherry, and this is porcelain.
White is porcelain.
Kind of looks like a tsunami curl.
I just a lot of things, and they're all sweet and good.
So we've been enjoying this great book by Gustav Hoffmann. Many of the sites we're seeing here in northern Oman are from his work, and of course he felt so special about this outcrop that he put it on the cover of his book. So why is this outcrop special? Well, first of all, it's very symmetrical and dramatically pleasing to the eye. They are deep water porcellanites, which are the white layers, and what appears reddish are the deep water radiolarian cherts. And upon scratching those cherts, it's really just red on the surface. They're really more of a dark gray or medium gray underneath. And a lot of people don't realize that. And we didn't either. So we're enjoying this particular outcrop, and then you can see how it's intensely folded. This is part of the betaine nap, and this is of the ophiolite sheets and the thrush sheets that we've seen. This is one not from the north, like the Somal ophiolite or the Hawasina nap. This is from the east. So this is 15 million years later, and this has got structurally deformed, and it is a incredibly photogenic outcrop, and that's why many call it the mother of all outcrops.
Hello, we're in Oman, here by the coast near the town of Sur, and we have a spectacular outcrop. It looks like a textbook diagram, and it's made of radiolarian cherts and porcellanites, and it's very, very admirable because of the symmetry of its chevron folding.
20 minutes, I'm afraid, because we just lost quite a bit of time in the day, and we've got 2 more stops after this. But this is the same Wahara formation as the last stop. The difference being that instead of just the red and white layers, we've also got these black layers. And these black layers are manganese oxide, is the mineral, or pyrolusite. And often in the deep sea, pyrolusite can form as nodules on the seafloor, but this isn't nodules. And basically, unlike manganese nodules that grow slowly on exposed sea floors, the manganese here formed within the sediment layers, then when dissolved manganese in deep ocean water precipitated as oxide under more oxygen-rich conditions. Changes in ocean chemistry, particularly oxygenation, cause manganese to be locked into certain beds, while adjacent layers record iron oxidation, the red chert, or high clay carbonate content, the white porcelainite. Anyway, I'm going to take you down to a really photogenic area, okay? And when I was here last year, they weren't doing any mining. The mining is kind of on and off.
We want to keep pointing at it?
Okay. Yeah. This is a pyrolusite layer. Good. Well, yeah, I recommend in some of this pure pyrolusite.
Does anybody know what manganese is used for?
Black layers is full of manganese oxide. And chromium.
Wow, this is beautiful.
This is
It's very much, it looks like that, but if you stand here and look along it, it's not folded at all. It's completely vertical.
We're very close to the last outcrop, which was the mother of all outcrops, the folded and thrusted porcelainite and radiolarian chert. And here we have more porcelainite and radiolarian chert. The porcelainite is the white layers, and the radiolarian chert are the red layers. And this outcrop is incredibly dramatic, the way it's weathered and cut. But if you look down the outcrop, you can see that the beds are flat. They're not folded. They're just eroded with the appearance of being folded. And as we walk and pan down this outcrop, what's really of interest are many layers that have pyrolusite, which is got manganese. So it's something that is being mined, and as you pan around you can see this big mine area for pyrolusite.
Many years and several years, and I come to the conclusion that this layer is the carbonatite, and a lot of this outcrop is something else. But anyway, carbonatite is an unusual type of volcanic rock made mainly of carbonate minerals rather than silicates, and this gives the rock its pale cream to light grey colour. Now, studies have shown that these carbonatites are exactly the same age as the kimberlites that we saw earlier on today, 141 million years old, and erupted during the breakup of Gondwana into an early opening Indian Ocean. These ages come from minerals crystallized directly from the magma. Now, that's the main thing I was going to tell you, is that this is a very rare lava that contains carbon in it. And there's only one volcano in the moment in the world, Donalongai in Tanzania, that is erupting this, where the East African Rift Valley is breaking up. But what we have around the corner as well, there's amethyst crystals. Most of the outcrop is this black material here, and I've just been thinking, I mean, I'm interested to know other people's opinion, but I'm thinking it's probably like a volcanic ash, something like that, and then you've got veins of amethyst in that just around the corner. But I would say that this is the carbonatite. This layer just here, this is a lava flow of this carbonatite lava. I mean,
Are carbonatites associated with basalt at all, or they're just this material?
are they associated with basalt at all? I think let's ask Hillary that question.
Yeah.
You have your acid bomb? Is this the
So here is amethyst crystals associated with the carbonatite. And it's a slightly pinkish purple.
And here is yet another one. This is made from carbonatite. Carbonatite is a very rare type of lava, which is very, very rich in carbon dioxide. In fact, there's only one volcano on the planet today that is producing it, Donalongai in Tanzania. And what it appears is, this is a volcanic ash that is carbonatite. And if we come over here, walking up here, this is actually the carbonatite lava. And carbonatite lava, unlike normal lavas, can be a white colour or a pale grey colour. And look here, you know, this is just really white. And this carbonatite has been dated to be exactly the same age as the kimberlite pipes that we were looking at earlier, 141 million years old. And it's all to do with the breakup of the supercontinent Gondwana, and it's somehow producing these poorly understood magmas which are incredibly rich in carbon dioxide.